This PowerPoint presentation is entitled Independent Samples T-Tests. The objectives are: the student will be able to describe when independent samples t-tests should be conducted and carry out right-tailed, left-tailed, and two-tailed independent sample t-tests. Independent samples t-tests illustrate a two-sample problem. We are interested in comparing the mean of one population to the mean of the other population. In this particular two-sample problem, it is imperative that the groups are independent of one another. Subscripts of 1 and 2 denote the population or sample to which a parameter or statistic refers. We have variable x sub 1, population mean mu1, population standard deviation sigma 1, sample size n1, sample mean x bar 1, and sample standard deviation s sub 1. We have corresponding values for our second population, denoted with a subscript of 2. Notice that we have two populations that we are going to compare. We might be interested in comparing the scores of men to women, or the scores of a treatment group to a control group. When we do a two-sample problem, again, this is called independent samples t-test. It is for use when we have two groups that we are comparing. We want to know if there is a difference in the population mean of those two groups, and the data are independent of each other. That means that participation in one group has nothing to do with who is in the other group. The hypotheses in two-sample problems are similar to the hypotheses in one-sample problem. The null hypothesis is mu1 equals mu2 versus the alternative mu1 is not equal to mu2 for a two-sided or two-tailed test. An alternative way of writing that same hypothesis is to say h0 mu1 minus mu2 equals 0 versus the alternative mu1 minus mu2 is not equal to 0. If mu1 equals mu2, then the difference in means is 0. Those two sets are equivalent for writing the null and alternative hypothesis. For two-sample problems, you can also have a left-tailed or a right-tailed test. The left tail has a less than sign, the right tail has a greater than sign. Note the difference in language between two-sided and two-sample. We have talked about a one-sample t-test that is appropriate when we have one single sample and we want to make a generalization about a single population. In that case, we could have two-sided, left-tailed, or right-tailed tests. Similarly, with the two-sample problems, when we have two populations that we want to compare, such as males to females, we have two-sided or two-tailed, left-tailed, and right-tailed two-sample problems. It is imperative to distinguish between one versus two sample and one versus two-sided. One sample means you have one sample of subjects. Two samples means you have two samples of subjects. Two-sided or two-tailed means that there is a not equal sign in the alternative hypothesis. Again, the difference between two-sample and two-sided, one sample and one-sided is important and should be reviewed. The test statistic for the two-sample case is slightly more complex in notation than the test statistic for the one-sample case. The t-test statistic is the t with n1 minus 1 plus n2 minus 1 degrees of freedom. Again, the degrees of freedom tell you the row of the t-table that the critical value will come from. Because we have two samples, we use n1 minus 1, the first sample size minus 1, plus n2 minus 1, the second sample size minus 1, as the row to get the critical values from. The value of the test statistic is found by taking x bar 1 minus x bar 2, the difference in sample means of the two groups, divided by the square root of sp squared over n1 plus sp squared over n2, where sp is the pooled standard deviation and sp squared is the pooled variance. The formula for computing sp squared is sum of squares for group 1 plus sum of squares for group 2 divided by degrees of freedom 1 plus degrees of freedom 2. Alternatively, if you're starting with raw data and computing summary statistics, you could compute the t-test statistic as x bar 1 minus x bar 2 divided by the square root of n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2 times the square root of 1 over n1 plus 1 over n2. As you can see, this formula is slightly more complex than the one sample t formula. However, the logic of carrying out the hypothesis test is quite similar. Consider the following example. A researcher is evaluating the pain relief effectiveness of a new medication by comparing pain tolerance for a sample of n equals 10 people who receive an inactive placebo to 10 people who receive the medication. The scores for the placebo group produce a mean of 38, and the sum of squares from the data is 150. The scores for the medication group have a mean of 42, sum of squares equals 210. Again, it is important to pay attention to the notation of problems. In this particular problem, we are given the sum of squares, which is the numerator of the variance formula. Are the data sufficient to conclude that the medication has a significant effect? Use a two-tailed test with alpha equals 0.05. We first state the null and alternative hypothesis. We were told to use a two-tailed test. So our null hypothesis is that the mean for the medication group equals the mean for the placebo group. Our alternative hypothesis is that the medication group mean is different from the placebo group mean, a not equal sign in the alternative. The research question asks whether there is evidence of an effect. The appropriate test in this case is a two-sample test because we have two samples, one sample from the medication group, one sample from the placebo group. Those two samples were not related, they are independent of each other, making the pooled independent samples t-test the appropriate test. And we were told to do a two-tailed test. First, we want to compute the pooled variance, which is denoted s sub p squared and is found by s sum of squares 1 plus sum of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2. In this case, 210 plus 150 divided by 9 plus 9, which turns out to be 20. The test statistic utilizes the value of 20 in the denominator. The test statistic is found by taking 42 minus 38, the two group means, divided by the square root of 20 over 9 plus 20 over 9, yielding a test statistic of 1.90. After we compute the test statistic, we compare the test statistic to the critical value as we have done in every test that we've computed. The process again, state the null and alternative hypothesis, compute the test statistic, which in some cases is a slightly more complex formula, compare the test statistic to the critical value, and draw a conclusion of the test. In this particular case, we have our test statistic of 1.90, and we have to compare that to our critical value. We were told to carry out a two-tailed test at 0.05. Therefore, we have to find the critical values that are at the two-tailed 0.05 column of the t-table. We are looking at the t with 18 degrees of freedom, where the 18 comes from the first sample size of 10 minus 1 plus the second sample size of 10 minus 1, or 9 plus 9, which is 18. Again, we are looking in the alpha of 0.05 for a two-tailed test, and we get our critical values of negative 2.101 and positive 2.101. We then compare our test statistic to those critical values, and we see that the test statistic falls in the do not reject region. The conclusion, therefore, is do not reject the null hypothesis because our test statistic of 1.9 falls between our two critical values in the do not reject region. Therefore, there is not evidence that the medication has a significant effect. We did not see a difference between the medication group and the placebo group. Note that decisions will be made based on p-values when we look at SPSS output of these types of problems. We can compute the effect size for problem 2, again with a similar formula as the effect size for the one sample case. In the two sample case, we take a look at the difference in means divided by the pooled standard deviation, x bar 1 minus x bar 2 divided by S sub p. This value of 0.89 or 0.9 standard deviations indicates again a large effect. The objectives of this presentation are: the student should be able to describe when independent samples t-test should be conducted. Independent samples t-test should be conducted when we have two samples of data and our goal is to compare the populations from which those two samples came from. It is imperative that the two samples are independent of each other. You should also be able to carry out a right-tailed, left-tailed, and two-tailed independent samples t-test. In order to carry out this test, you state the null and alternative hypothesis, which in this case will involve mu1 and mu2. You then compute the test statistic, which is slightly more complex than the test statistics that we've looked at so far. Once you have computed the test statistic, you compare it to the t critical value. The row of the t table to compare the critical value from for the two sample case is the t with n1 minus 1 plus n2 minus 1 degrees of freedom. We compare the test statistic to the critical value and draw a conclusion of our test. For the two sample case, the conclusion relates to whether the population means of the two groups in question are equal to each other versus not equal, greater than, or less than.